The objective of the experiment is to measure the distance dependence of the magnetic field due to a small bar magnet and compare the measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the Biot-Savart law. According to the Biot-Savart law, the magnetic field should follow the formula below. The formula states the magnetic field is inversely proportional to the distance cubed. As a result, we can use this relationship to predict the magnitude of the magnetic field. This was accomplished by using software on my phone called Teslameter, which is a magnetometer app, to measure the magnetic field due to the permanent dipole magnet. In order to successfully do this, we have to compensate for the magnetic field of the Earth, specifically the northern magnetic field. This is achieved by orienting the phone in such a manner that causes the x component to be 0. Once this is accomplished, the permanent dipole magnet is positioned relative to the sensor so that a magnitude of b sub x ranging from 20, 70, 120, 170, and 220 microteslas is produced, and the distance at which each measurement is received is recorded 3 different times and averaged. In order to identify the relationship between distance and magnetic field, the Biot-Savart equation has to be rearranged to show the linear relationship. The magnetic field of the dipole is equal to mu naught over 4 pi quantity multiplied by 2 mu over distance cubed. Set k equal to mu naught over 4 pi times 2 mu. Therefore, we can rearrange the equation substituting in k and then using the natural log to get the final equation, which states the natural log of the magnetic field is equal to natural log of k plus n times natural log of distance. Now we can graph and look for the n value, which will be the slope of the line of best fit. On the graph, the slope is negative 3.1, which is close to the expected value of negative 3. Now that the linear relationship has been found, we can also calculate the magnetic dipole moment. As supported by the graph, natural log of k is equal to negative 17.606. This means k is roughly 2.3 e to the negative 8. Following the math on the screen, u is calculated to be 0.11 a meters squared. Closed grip modeling is used to compare experimental versus computational results. The blue arrows represent the magnetic field on the perpendicular axis. The orange arrows represent the magnetic field on parallel axis, and the green arrow represents the magnetic field at a 45-degree angle. Although the experimental results supported the expected distance dependence of the magnetic field, there are errors in the experiment as supported by the discrepancy between the model and experimental results, most clearly shown by the x value of the model, 1.2 e to the negative 6, being half that which is found in the experiment, which is 2.4 e to the negative 6. This is because the model only takes into account the magnetic field produced by the magnet, when in reality there is much more interference, such as from Earth or electronics in the area. When conducting the experiment in a non-perfect lab setting, such as my kitchen, with technology such as my cell phone to record data. In conclusion, as the magnetometer moves closer to the magnet, the x component of the magnetic field increases. The magnetometer is very far away. It measures a non-zero magnetic field in the x direction. You need to subtract the b Earth for the y-axis value to find the Earth's magnetic field. The experiment shows there are a distance dependency relationships with the position of the magnet and the magnetic field, recorded with an experimental n equals negative 3.1 when n is really negative 3. Question 1. The answer. When compensating for magnetic north, we ensure the magnetic field of the magnet is the only field measured. If this wasn't done, the Earth's magnetic field would also be included in the measurements, causing the interference in the x values measured, causing the experimental result to be far less accurate. Question 2. Answer. The magnetic field would increase by less than double of the original value, but it would still be in the same direction.